All right, so now we'll start the lecture notes for Chapter 17 in your textbook. And this will include just some basic introduction to concepts of diffusion, how it's measured, how it's defined, and some elementary molecular theories that are used to predict or estimate diffusion coefficients, because these are very helpful from a practical point of view. So the important thing to understand is that light viscosity and thermal conductivity, diffusion coefficients for mass transfer are or were originally empirically based, defined on an empirical basis based on observations in the laboratory of natural phenomena. This is the way Fick formulated the laws of diffusion, as we'll see in just a few minutes. And so I'd like you to consider a simple experiment that's used to that can be used as a basis to understand how diffusion coefficients are defined. And so we have a plate of fused silica Pyrex glass, and it turns out that this Pyrex glass is not entirely without pores or pathways for gas molecules to diffuse through it. However, those pathways are extremely small, so nitrogen essentially will not dissolve or diffuse through the Pyrex. This distance, the thickness of this, will be on the order of microns, for example. However, helium will. And so we consider a case where we have a sheet of this material with nitrogen flowing on both sides of it. And at some time t equals 0, we switch the gas from nitrogen to helium down here. The helium will actually dissolve or partition into the fused silica at y equal to 0 at a mass fraction of WA0, whatever the equilibrium solubility is. It's actually quite low, as we'll see in a moment. And then there's a gradient in concentration of helium between the two sides of this fused silica, and over time, as the helium works its way through this material, there will be a buildup of a concentration gradient, and at steady state, for all intents and purposes, that concentration gradient will be linear, going from the solubility of helium in fused silica on the downstream side up to concentration of 0 or mass fraction of 0 on the upstream side, since all the helium that diffuses through this plate is swept away by the flowing nitrogen gas. And we will treat this as a binary mixture. The nitrogen cannot access the material, and so the binary mixture is helium and fused silica, where component B is the silica. And if you do this experiment at a number of different thicknesses and at a number of different gas pressures of helium, which will change the concentration of helium dissolved in the silica, typically that would be a linear relationship. As you double the pressure down here, you would double the mass fraction of helium dissolved in this material, and so on and so forth. You would find, and you measure the flux of, of helium through this plate at steady state, you would find that all of the experimental data could be included or accounted for by a model that looks like this, where the flux of helium through this silica plate could be written in terms of the difference between the concentration of helium at the upstream and downstream sides of the plate divided by the plate thickness. Rho here is the helium silica system density, and you can see that if you multiply rho times the weight fraction of helium dissolved in the system, that's just going to be the concentration of helium in the plate. And so this will just be the concentration difference in helium between the upstream and downstream sides of this plate. And if you vary L and you vary W sub A, you'd find that all of the data could be explained by an empirical model of this form with a constant value or nearly constant value of this parameter DAB, which we call a diffusion coefficient. And so this is an engineering definition of diffusivity based upon measuring the flux for a given concentration difference and in a given thickness. Now, on a differential basis, We can write that as shown here, and this becomes what you would recognize as Fick's first law of diffusion. If the density is constant, you might replace this mass fraction, W sub A, in the boxed equation with simply the concentration gradient in helium through that system. We will come back to this concept of average velocity, but I want to just go ahead and introduce it here while I'm on this slide. The average velocity of the mixture through the silica plate is given by the weight fraction of each component, the helium and the silica, multiplied by their velocities. Now it turns out that the silica component B is not moving, and so that will be 0 in this particular case. But this is a general definition of a so-called mass average velocity, and that turns out to be important for us a little bit later. Generally, the mass flux can be defined as follows, and this is looking a little more looking a little bit away from the problem we're just talking about. This is an aside, essentially, where flux can always be written as a product of concentration. You can work the units out here for rho times WA, and it's in terms of concentration. Flux can always be written as concentration times velocity. And the important thing to know about diffusion is that it is measuring the velocity or the flux of a component relative to always to a frame of reference, and in this case that frame of reference is the mass average velocity v sub y. Now the reason for this is that you don't want to include phenomena in diffusion, that is phenomena that might affect the value of the diffusion coefficient, that really have nothing to do with diffusion. For example, if I were to take this plate and keep everything in terms of the experimental conditions exactly the same, but now start raising that plate at 1 meter per minute, then we would not want, and measuring the flux relative to fixed coordinate systems, we would not want the mass flux of helium coming out of this device to be, at least the diffusive part of it, to be impacted by how fast this whole piece of silica is moving or not. And so the diffusion is always measured relative to a frame of reference or relative to an average velocity of the system. And so the way to look at this is, another way to think about it is if you have dye in water flowing down a pipe, and let's say you're near the center of the pipe where the velocity profile is almost constant in a radial direction, and you start to measure or track the diffusion of dye into the water surrounding it. The diffusion coefficient of the dye is going to govern into the water, is going to govern how rapidly the dye is moving relative to the water. It's not going to be the absolute motion of the dye, because it's being dragged along by whatever the convective forces are that are pushing the water through the pipe. And so the diffusion phenomena is that portion of the mass transfer that's above and beyond the motion of the system as a whole. And so that's why we always write the diffusive flux relative to a reference velocity. Turns out there's more than one reference velocity that can be used. We'll come to that in a moment. We can also define the mass flux of the silica, the component B in this case, analogously. And because if you imagine, think back to the water and dye flowing through a pipe, the diffusive flux is measuring the relative flux of one component to another. And so if the dye is moving forward relative to the frame of reference of the fluid moving down the pipe, then that necessarily means that the water in that same diffusive frame is moving backwards. And so in order to maintain mass balance, we have to require that these fluxes sum to zero. And otherwise, the definition of total flux on the next slide or so is not going to be correct. And so, generally, in differential form, we'll write the flux as shown at the bottom of this slide. And so, this is in vector form. We can come back to the problem we were looking at and use physical property data from the literature. So if you have a plate that's 10 microns thick and the density of the silica is essentially 2.6 grams per cc, that of pure silica, the diffusion coefficient is reported in the literature for helium through silica, 10 to the minus 8 square centimeters per second. If those numbers mean anything to you, that's fairly quick for diffusion of a molecule through a solid piece of glass. This is the solubility at 1 atmosphere partial pressure, the amount of helium that will dissolve in that material, and here's the thickness, and so you can calculate what the flux of helium would be through that glass plate, and it would be about 10 to the minus 11th grams per square centimeter per second. We can calculate the average helium velocity then using this result. I'll show you the magnitude of these terms. And if we evaluate the velocity of helium at the bottom of the plate, we can rewrite this expression as shown here. We have an expression for the flux, we have the density of the system, and Vy0. So we rewrite the mass concentration of the helium can be expressed in terms of the density and the mass fraction of helium, and we can calculate this velocity of helium at the bottom of the plate. We can calculate the average velocity using the definition of average velocity, and what we find then is that the mass average velocity in this system is on the order of 10 to the minus 12th centimeters per second. The velocity of the helium is on the order of 10 to the 5th centimeters per second. So the fact that the silica is not moving and that there's very little helium dissolved in that plate means that the velocity of the helium is really doing the bulk of the movement in this system. However, it is important to know that if you are moving a component through that glass plate, even though the glass plate isn't moving, the center of mass of that system does move a little bit based upon the velocity, the mass fraction of helium and the velocity of helium. And so in the experiment that we discussed, it's reasonable to neglect these types of contributions, so-called convective or frame of reference contributions, to the flux of helium through the membrane, and the corollary to that is that the flux in the laboratory fixed coordinates is a very good approximation of the diffusive flux in this system. There's essentially no frame of reference or convective effects that are of significance. Now I'd like to just look briefly at, this is a reproduction, translation of Adolf Fick's early paper where he published on what became known as Fick's law of diffusion. And I want you to see how this works, to see how as you begin your research careers or continue your research careers here at the University of Texas, how this, the benefits of reading broadly and being able to take information from one field and apply it to another. And so Fick is talking about work that was published by Sir Thomas Graham investigating the diffusion of salt in water. So Sir Thomas Graham was studying basically the migration of salt from low concentrations, high concentrations to low concentrations in water, and reporting phenomenologically the results that he got. And Fick says, it appears to me a matter of regret that in such an exceedingly valuable and extensive investigation, the development of a fundamental law was neglected. Don't see that in the modern literature too often. And the next paragraph, I think, is the most striking. It was quite natural to suppose that this law for diffusion of a salt in its solvent must be identical with that according to which the diffusion of heat in a conducting body takes place. Upon this law, Fourier founded his celebrated theory of heat, and it is the same which Ohm applied with such extraordinary success to the diffusion of electricity in a conductor. And so Fick is using an analogy with Fourier's law in heat conduction, Ohm's law of conduction of electricity, as the rationale or the justification for what he's about to propose as Fick's law. And you'll recall, for example, in Fourier's law that heat flux is proportional to the thermal conductivity times the gradient in temperature, and he's about to propose that mass flux is proportional to the gradient in concentration. According to this law, the transfer of salt and water occurring in a unit time between two elements of space filled with differently concentrated solutions must be directly proportional to the difference of concentration and inversely proportional to the distance of the elements from each other. That is, the flux is proportional to the concentration gradient. And he's proposing this in analogy with Fourier's law of heat conduction and Ohm's law of electricity. And if you go on, he talks more about the mathematics of it and on to analyze Graham's results. But if you look at the result that's in red here in equation 2, if you, the deltas here now we use as differentials, y is concentration. He calls minus k is the parameter he gives for the diffusion coefficient. We will label that DAB nowadays. And so this is the way that Fick's law was first proposed. It's based on empirical evidence, and it was based on analogy with Fourier's law and Ohm's law. It's a pity we weren't first, and they couldn't do it based on our work, but that's the way it goes. And I think it's important as you go forward in your work that you understand how large or small diffusion coefficients are, because the flux is directly proportional to diffusion coefficients. And it turns out that there are some simple rules of thumbs that are helpful. In mixtures of gases, by and large, diffusion coefficients, and we typically will express them in square centimeters per second. I am not a slave to SI units, and I understand what these mean in centimeters squared per second. So that's the units we'll typically use. In gas mixtures, diffusion coefficients are often similar, and they're often of the order of magnitude of about 0.1 square centimeters per second in round numbers. So you can carry that with you as as just a good rule of thumb. In gas mixtures, diffusion coefficients are about 0.1 square centimeters per second. In liquid mixtures of a variety of different types, they're typically of the order of 10 to the minus fifth square centimeters per second. So 0.1 square centimeter per second in gas mixtures, and liquids of the order of magnitude of 10 to the minus 5 square centimeters per second. In a more dense media, diffusion is slower. Remember, this is random molecular collisions occurring, and in a low density gas phase, the molecules go further between collisions, and so the diffusion coefficients are higher. In the liquid phase, where the density is 1,000 times greater, the distance from one collision to another, one diffusion step to another, is markedly reduced, and so the diffusion coefficients are reduced along with it. Now, when you get to the solid state, the situation gets really goes all over the map. And so as you get to diffusion, say, of gases in these inorganic solids, now you see numbers down in the 10 to the minus 10th and 10 to the minus 11th. When you talk about metals diffusing through other metals, you see numbers now that go from 10 to the minus 8 to 10 to the minus 30. So just literally over orders and orders and orders of magnitude. And so there's not a general rule here or a general rule of thumb for what the value of those diffusion coefficients might be. We'll talk a little bit about some of the molecular theories that are used to describe the diffusion coefficient. This is showing a plot of corresponding states type plot for diffusion coefficients in gases, and essentially it's showing the dependence on reduced temperature and reduced pressure. Plots like this, you'll find this in your textbook, but plots like this are used to estimate diffusion coefficients from correlations. I work in polymers, so I have to show you some diffusion coefficients of polymers, and this is gases diffusing through two different classes or two different types of polymers. One is polysulfone, which is used in air separation. It's a hard, rigid thermoplastic, very low levels of mobility. Diffusion coefficients as you go from helium up to butane change by about 8 orders of magnitude or so, with the larger molecules going much more slowly than small molecules. Silicone rubber is, you would know this as bathtub caulk or window caulking at home. It's also used as a membrane material. It's a very flexible material. There's almost no barrier to rotation about this silicon-oxygen bond, so it's a very highly mobile material due to just thermal thermal motion at room temperature, diffusion coefficients are higher, and there's not nearly such a strong change with the size of the penetrant, here characterized by critical volume. I'll come back now to work that's in your textbook just to give you some of the primary guideposts that are used to estimate diffusion coefficients. There's an excellent book called Properties of Gases and Liquids, where you'll find state-of-the-art correlations for many types of transport properties, including diffusion coefficients and when to use certain correlations in certain cases. These I'll take from your textbook, and references here to figures will be references to figures in your textbook. And so for binary gas diffusion at low pressure, the diffusion coefficient is inversely proportional to pressure. That's that proportionality to gas concentration and the distance between the molecules. As the pressure goes up, the molecules come closer together. Their distances between collisions go down, and the diffusion coefficients go down proportional to that. It also depends upon the critical pressure and critical temperature, as well as the molecular weight of the components. And this brings in dependencies on the strength of the interactions between the molecules, as well as their size. There's some caveats about how to fit what values of these parameters to use, and how close it is to experimental data. Yes?
That last equation, is this just an empirical equation? Because the units here don't work out to be centimeters squared per second for the diffusivity.
Well, they need to. The units on A need to be whatever they need to be to make these units work out.
Okay, so A isn't dimensionless?
Right.
Yeah.
And it is developed from kinetic theory and corresponding states arguments. That doesn't mean that it comes directly when it's developed. Often these things are developed in analogy with basic theoretical arguments adjusted for so that they fit the experimental data well. So the diffusion coefficients of binary mixtures of nonpolar gases can be predicted to within about 5% from just simple basic kinetic theory. And I'll go over this just briefly. I'm not going to belabor it, because I'm really much more interested in teaching you how to solve problems, and the strategies behind that. But I want to at least you to know where to go to look up values of diffusion coefficients if you need estimates of them. And the kinetic theory results you'll find in several places in your textbook. It's first discussed at the very beginning when they talk about it from a point of view of viscosity. Later, when it's discussed in the section on the textbook when they talk about heat transfer and thermal conductivity. And then it's discussed again in the mass transfer section. So to get at all of this, you may need to refer to several parts of your textbook. And the basic idea in kinetic theory is that you have a large volume of gas A, and a few of the A molecules are labeled. We call them A star. So we're measuring essentially what would be called a self-diffusion coefficient in this case. And these molecules are all identical except for the labeling. They're rigid spheres of equal mass Ma and diameter d sub A. And we want to calculate the diffusion of A through a sea of other A molecules. We use basic results from kinetic theory. I won't belabor the derivation of these, but the mean velocity of a molecule or particle depends on the temperature and the molecular weight of the species, as shown here. The average wall collision frequency per unit area is given from kinetic theory by 1/4 N, where N is the molar concentration of gas molecules times the mean speed. And we'll also define the mean free path between collisions, lambda, and that depends upon the concentration of the gas and the square of the diameter. Again, these are standard results from kinetic theory. I won't belabor them. And for an ideal gas, the concentration N is just the pressure divided by RT times Avogadro's number. Pressure divided by RT would normally give you gas concentration in an ideal gas in like moles per cc, for example, and then multiplying by Avogadro's number puts it on a per molecule basis. And the scenario we consider is one where there's a concentration gradient in species A, as shown here. We consider it to be linear and over distances that are short enough. This is an absolutely excellent approximation. And we consider a gas molecule that has reached this plane Y since its last collision some distance away. And it turns out that on average, that distance from the last collision is about 2/3 of the mean free path to account for the fact that these collisions can send this molecule off in random directions. And so we consider the motion of molecules of species A in the y direction under a mass fraction gradient with the fluid moving at a velocity of Vy. So that'll be the reference velocity in this particular case. Take temperature and total mass concentration in grams per cc is constant. And the total flux of component A in the y direction then is the sum of the transport due to the fact that the fluid itself that has A in it is moving in the y direction. That's just the concentration of A, rho times W sub A times the velocity. Flux is concentration times velocity gives flux, gives units of flux. And so this is the convective portion of the velocity. And then this is the portion we'll be interested in from kinetic theory. That's the part of the transport that's above and beyond convective motion. That's just due to the presence of the concentration gradient and the molecular diffusion of the species among one another. We can write the transport of component A to Y due to molecular motion of A, essentially taking the concentration, how many molecules of A per unit volume there are, times their speed. The factor of 1/4 comes from essentially this the average wall collision frequency. So what you imagine is that coming to Y, we imagine these gas molecules essentially, quote unquote, colliding with this virtual plane at Y. And the number of those that do that coming from below is given by 1/4 rho WA is the average velocity evaluated here, and the number that are going away from this plane Y is given by a similar expression. We then take the mass fraction of A in the y direction to be a linear function of the linear function of distance, and the distance A here has been replaced by 2/3 lambda based upon this relationship. And so now we can combine those two relationships to get the expression for the flux. And we recognize that this has the form of Fick's law if this grouping of terms, average velocity times the mean distance between collisions is the diffusion coefficient. So if we identify that grouping, they basically make this look like Fick's law, then the diffusion coefficient in kinetic theory turns out to be written in the following form. We plug in the values for the average velocity as well as lambda, and the final result is shown here. And so it depends on the diffusion coefficient gets smaller as the size of the molecule gets larger, as the density or pressure goes up, and the diffusion coefficient gets larger according to the square root of T. And so this gives you an idea of the result from kinetic theory. This result is extended for diffusion of molecule A into a sea of rigid spheres of type B, which have a different size of that from A. I won't go over the derivation. This is just the final result from kinetic theory, and you can see it looks quite similar to the self-diffusion result, except now there's a slight change here in including the diffusion or the diameters of both components and the molecular weights of both components. And this gives surprisingly good results. It's very simple, but gives surprisingly good results within about 5% or so for gas mixtures at low pressure. And so, as you might recognize, these this type of picture doesn't account for any intermolecular forces, and so there are more sophisticated statistical mechanics descriptions of that do allow for attractive longer range interactions. The Chapman-Enskog model is one that is developed specifically to include those types of interactions. And you'll see that the diffusion coefficient result that it gives vaguely resembles the one from the simple kinetic theory without long-range intermolecular interactions, with some of the Lennard-Jones parameters starting to show up. These are parameters from the Lennard-Jones potential energy model. And omega here is a so-called collision integral, and values of this are tabulated in the appendix of the text. And it has a value of 1 for rigid particles, and then it's essentially describing a correction factor describing how far molecules deviate from being perfectly rigid. The collision integral is a function of kT over the Lennard-Jones well depth parameter epsilon, and those parameters, epsilon and sigma, in the Lennard-Jones model are calculated as shown here. And parameters for the Lennard-Jones well depth and Lennard-Jones size for a number of compounds of interest are given in a table at the back of your book. So this ties back to the familiar Lennard-Jones model of potential energy. And so those are some of the key guideposts in models that are used to predict diffusion coefficients in gases. Now, we'll say a lot less about liquids simply because there's a lot less known about how to predict diffusion in liquids. And as the reason that the previous simple models work in gases is because the gas molecules, if they're far apart and they have relatively rare interactions with one another, these long-range interactions, although important, are not dominant, and so simple models can capture most of the physical behavior. Let's see if it's going to like that. In liquid systems, the molecules are in much closer proximity. The density of liquids is about 1,000 times that in gases often, and the molecular understanding and models available for this are not nearly as well developed. A common approach, which is based on hydrodynamic theory, starts from the Nernst-Einstein equation, where the diffusion coefficient is related to the average velocity of a particle A through a mixture of A and B, and the mobility of that particle is this ratio of the velocity of the particle divided by the force that's being applied to it. And in Einstein's view, this force is supplied by the bombardment of solvent molecules colliding with the particle. In other words, that there was always a force applied through the thermal motion of the molecules relative to one another, and that force resulted in a velocity. And the proportionality constant, if you rewrite this with the force on the left-hand side and everything else on the right-hand side, the proportionality constant between the force and the velocity is kT over what's being called the diffusion coefficient. And Einstein considered the very simple case of Stokes flow, which you would have solved or seen in fluid mechanics. So you have a spherical particle in laminar flow through a fluid. The force on that acting on that particle depends on its radius, the viscosity of the surrounding media, and the velocity of the particle. And with this model for the force, the diffusion coefficient, of A through B can be written as kT over 6 pi times the radius of A and the viscosity of B. This is a very, it's essentially a precise equation for calculating, for example, the diffusion coefficient of a 0.1 micron latex bead through water. You have the viscosity of water, the radius of the beads, you get the diffusion coefficient just perfectly. Einstein imagined or derived it within this context. For the diffusion of liquids in liquids, the theory is not nearly as well developed, and I've given, there's correlations like the Wilkie chain correlation that you may have heard of to calculate diffusion coefficients of liquid A and B, and this is essentially an empirical correlation that works fairly well. But essentially, the diffusion coefficient of A in B depends on the viscosity of the mixture, the size of A, this is the molecular volume of A or molar volume of A, the molecular weight of B, and then a parameter psi, which depends on, is an association parameter, and it gives some indication of how much the components tend to associate with one another. So components like mixtures of hydrocarbons would have very low association parameters, and components that have strong hydrogen bonding like water and alcohol would have higher values. So this is a common first cut way to estimate diffusion coefficients of liquids and other liquids. Again, this course will not focus on transport in polymers, but I always dip back into it from time to time. It's a personal weakness. And the picture for diffusion of small molecules like gas molecules or water and ions through solid polymers is that the polymers have in their amorphous or disordered regions, they have gaps between the polymer chains that are sufficiently large to allow the penetrant molecules to exist there. Small gas molecules might be vibrating inside these gaps at like 10 to the 12th times per second. The polymer chains, because they consist of long chain molecules that are interconnected with one another, have much slower rates of molecular motion. And so from time to time there'll be random molecular motions that will open pathways from one of these gaps to another, and if the penetrant goes through that and this gap closes back up, then that penetrant will have taken a diffusion step. This mechanism is referred to in the literature as the Red Sea mechanism of diffusion. This is another view of that. I won't belabor it here. The types of motion that give rise to those local segmental dynamics along, for example, a polyethylene molecule where these balls represent CH2 units are shown here in so-called crankshaft motion. This is a picture of molecular dynamics simulation of diffusion of oxygen and nitrogen in a polymer poly-2,6-dimethyl 1,4-phenylene oxide. The type of polymer is not really important, but the picture that I want you to see is. And in this molecular dynamics simulation, polymer chains have been built at their experimental density, and they are imbued with kinetic energy, and then oxygen and nitrogen molecules are turned loose, and Newton's law of motion are solved over the system for long periods of time. And this is tracing the diffusion or the migration of one oxygen molecule. And you can see that it spends a long time in one of these gaps, like shown here. It spends most of its time there, occasionally leaving and coming back. But over time, gradually the oxygen molecule by random molecular motion drifts away from its starting point. It turns out in the same simulation, nitrogen only executes about one diffusion step, whereas oxygen executes 3. Oxygen is just a tiny bit, a fraction of an angstrom smaller than nitrogen. It's 3.46 angstroms in kinetic diameter. Nitrogen is 3.64. 4.6 versus 6.4, 0.18 angstroms difference in size. Nitrogen is about 0.18 angstroms larger than oxygen. And that small difference in size gives rise to a threefold difference in diffusion coefficients. Now this is just simulation, but if you go and measure these diffusion coefficients in the laboratory, that ratio is also 3 to 1 for oxygen and nitrogen. It means that oxygen can get through a slightly narrower channel in that material than nitrogen can, and the narrower channels, the smaller gaps come open more frequently just because they're energetically less expensive to create. We're going to probably end up a little early today because I just want to go over some basic definitions of concentration and flux and so forth. What we're going to use for the symbol rho sub A will be the mass concentration of species A in a mixture. So this will be like grams of A per cc of mixture. Its molar analog, C sub A, will be the moles of A per liter of mixture. And these two are related, of course, by the molecular weight. The total mixture density, which we'll also use in a number of the theoretical results and models that we'll be using, is just the sum of the mass concentrations of all of the components. And the mixture molar density likewise is the sum of the molar concentrations of all of the species. Weight fraction, I think you'll be familiar with, is the mass concentration of one component divided by the total mixture density, and likewise for mole fraction. So these are just basic relationships we'll use because we'll be converting between concentration units, both mass and molar basis, as we go through a number of the problems that you'll be working. There are a couple of predominant average velocities that are in use. The mass average velocity is given as follows. It's the velocity of each component in a system multiplied by its concentration, its mass concentration, and then divided essentially by the density of the total mixture. And that simplifies down to the velocity of each component weighted by its weight fraction. The reason this velocity is important is that we're going to come in a few weeks to solving problems where there is convective fluid flow that's governed, for example, by the Navier-Stokes equations. And the Navier-Stokes equations, the velocity that appears in there for mixtures is the mass average velocity. And so that's one is important for us. The molar average velocity, in many problems in diffusion, we talk about moles, say, of gas going through a catalytic particle and things like that. And so often these calculations are done on a molar basis, and so the molar average velocity is also an important one for us. And it's written analogously as the concentration of each species times its velocity divided by the total molar concentration. And that works out just to be the mole fraction weighted velocity of each component. These two velocities are not necessarily equal to one another if the molecular weights of the components are not equal. But in many cases, as we'll see, they're close enough to one another that when we start to couple fluid mechanics together with mass transfer, we can replace this one with this one. But we'll get into that a bit later. In binary systems, the mass flux due to diffusion, or the mass average diffusion flux, is by definition the concentration of A, rho sub A, times the velocity of A relative to the system average velocity. And this emphasizes the point that diffusion is always the motion of a component above and beyond what the overall system is moving at, or the convective velocity. And that typically is the motion due to concentration gradients. And this is the expression that we connect with Fick's law, as shown here. We can also define a molar average diffusion flux similarly, but based on molar concentration, and write the equivalent form of Fick's law as shown here. You'll find in your textbook other types of average velocities and diffusion flux defined based on those average velocities. These are not the only two that we can pick, but these are two of the most common. the total mass flux of a system, N sub A, is the essentially the mass flux of a component relative to a fixed set of coordinates. It is the concentration of A times the velocity of A, and that turns out to depend on the diffusive flux of A plus the flux of A that's due to the bulk motion in the system. So these would be so-called frame of reference or convective effects. When we get a bit later and start to solve problems where we have both diffusion and convection occurring, there will be times when we'll make an engineering judgment, for example, that diffusion is much more important to the flux than convection, so we'll neglect this. In other cases where diffusion will be much less important than the convective flux, and so we'll modify the total mass flux expression depending on what the dominant mechanism is for mass transport. You can use this expression then to write the diffusive flux in terms of the total mass flux of A and then the convective part, and you can see that if you write this out for A and B, that those fluxes have to sum to 0. Likewise, the total molar flux is defined based on the molar concentration times the velocity of A, and we have similar definitions for the relationships among these flux terms that in a binary system, if the flux of A is positive, the flux of B is negative, and they have to exactly offset one another to preserve these definitions. I'm going to stop the presentation here.